You clicked because you want to understand AI platform engineering, but your model works in notebooks, yet crashes in production every single time. The real problem is that MLOps treats silicon like generic storage when it is actually the hardest bottleneck of all. You will learn why ignoring hardware limits causes 44% of scaling failures and how to fix them before they destroy your deployment pipeline. Every junior engineer knows the story. You train a model in Jupyter, everything looks perfect, you wrap it in a container, push it to Kubernetes, and suddenly the inference latency spikes or the GPU memory fills up instantly. The standard advice is to check logs, restart pods, or increase resource requests. That approach works for CPU-bound tasks but fails completely when dealing with accelerators like GPUs, TPUs, or ASICs. This happens because MLOps was built as a process layer that assumes hardware resources are infinitely divisible and interchangeable. In reality, the physical silicon running your models has strict laws of physics that no amount of orchestration can override. Let us look at what is actually happening under the hood when things go wrong. Major reviews identify operational complexity as the primary cause for production failure, with 44% of organizations embedding AI yet struggling to scale significantly. But this statistic hides a deeper truth about where those failures originate. The root cause often lies in a disconnect between process layers and silicon realities. When you treat a GPU simply as another pod resource without understanding its memory bandwidth or tensor core capabilities, you are setting up an inevitable collision course with physical limits. Consider how modern training frameworks interact with hardware. They assume that compute cores can be fully utilized if the software is correct. But in practice, robust architectures define strict resource limits and requests in Kubernetes to prevent exhaustion on constrained edge nodes, precisely because cloud control planes and on-premise inference engines possess distinct physical capabilities. If you do not account for this distinction, your system will fail when demand exceeds what the specific silicon can physically handle at that moment. The orchestration layer sees a busy node but does not know if it is saturated by memory bandwidth or thermal throttling. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Here is the thing about MLOps failures that most tutorials ignore. Successful scaling requires explicit hardware awareness because robust architectures define strict resource limits and requests in Kubernetes to prevent exhaustion on constrained edge nodes, acknowledging that cloud control planes and on-premise inference engines possess distinct physical capabilities. When you deploy a model without profiling its memory footprint first, you are asking the system to guess how much high-bandwidth memory is needed. That guessing game leads directly into instability when models outstrip physical capacity. The container restarts because of an out-of-memory error, but the engineer sees only a generic pod failure and never connects it back to the specific silicon bottleneck that caused it. Now consider what happens during inference latency spikes in production. These frequent performance drops are often caused by suboptimal tensor core utilization and PCIe bus contention between host and accelerator. Issues like these cannot be resolved simply by container-level autoscaling without hardware-specific kernel tuning or model quantization strategies. You might see the system scaling horizontally, adding more pods to handle traffic, but if each pod is fighting for bandwidth on a shared PCIe bus, you are just piling up contention rather than solving it. The latency spikes because data cannot move fast enough between the host CPU and the accelerator memory, regardless of how many containers you spin up. This creates a critical gap in how we approach platform engineering today. Hybrid AI platforms succeed only when they enforce hardware-aware placement policies that match model tensor precision requirements to specific silicon capabilities, such as mapping FP16 workloads to Ampere or Ada GPUs while avoiding TPU incompatibilities. Relying on generic load balancing is not enough because different chips have different strengths and weaknesses in how they handle matrix operations. If you send a workload designed for tensor cores onto hardware that lacks them, the performance collapse can be catastrophic even if the theoretical compute power seems sufficient on paper. The productionalization gap in MLOps is often a hardware visibility gap, where engineers optimize for container restart rates and pipeline throughput while ignoring physical thermal throttling and power capping limits. These invisible constraints force models to run at 40% of their theoretical peak performance. Yet the metrics dashboard shows everything is healthy because no one was monitoring temperature or power draw in real time. You are optimizing for uptime, but not for actual utility. The model is running, it is responding, but it is doing so far below what the hardware could deliver if you had designed around its physical limits from day one. This leads us to the most important shift required in our field right now. Successful AI platform engineering requires shifting from a container-first mindset to a silicon-first architecture where the deployment pipeline includes hardware profiling stages to validate memory footprint and interconnect topology before any model is served. This prevents catastrophic scaling failures in multi-tenant environments by ensuring that every workload knows exactly what it needs before it ever touches the network. You must profile your models for memory bandwidth saturation, tensor core utilization rates, and PCIe bus contention as a standard part of your release process. If you skip this step, you are essentially building a high-performance race car with an engine tuned for lower-octane fuel and then wondering why it cannot reach top speed. The platform engineer's role is not just to orchestrate containers, but to understand the physical constraints that define what those containers can actually achieve. By integrating hardware profiling into your CI/CD pipeline, you catch these issues early when they are cheap to fix, rather than discovering them during a production incident when latency spikes and users abandon their requests. The path forward involves treating silicon not as an abstract resource, but as a specific architectural bottleneck that dictates system design. You need benchmark data that directly correlates hardware ignorance with specific failure modes in production, even though current literature largely treats hardware as a generic resource rather than a specific architectural bottleneck lacking such quantitative evidence. Until we generate more empirical data on how often MLOps initiatives collapse specifically due to unoptimized tensor operations versus general pipeline errors, the argument for hardware awareness must remain a necessary condition for scaling that acts in tandem with broader socio-technical challenges. But you can start today by changing your perspective. Stop asking if the pod is running and start asking what the silicon is doing when it runs. Check memory bandwidth saturation before deploying to production. Understand tensor core utilization rates for your specific model architecture. Verify PCIe bus contention limits on your infrastructure stack. These are not optional optimizations. They are fundamental requirements for building systems that actually scale in the real world where physics matters more than orchestration logic. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.